Hi guys, and welcome to part 4 of the interactive fog tutorial series. So in the last part where we left off, we had the ability to define a height fall off from distance fields from our scene capture and from the active fall off. And in this one I want to talk about adding some noise and some self-shadowing. So it's important to do that at this stage because one, adding the noise will actually allow us to visualize our self-shadowing much better, and then having the self-shadowing in now means that when we implement our interaction, we'll actually be able to see those finer details in the fog and actually see what's going on. Because without the self-shadowing, it's actually very difficult to see, which I'll demonstrate in a minute when we take a look at what's changed. And then after we've looked at what's changed and played with a few of the parameters, I want to quickly just talk about the theory of the self-shadowing and how that works, so that when we come to implement it, you'll have an understanding of that and why we're doing it the way we're doing it. And then we'll go and we'll break down everything as we did last time, look at how I implemented it, and I'll talk you through it. So in terms of what's changed, as you can see, our fog now has a noise to it. This has some flow to it, but we're not actually implementing the full flow in this episode because that's actually going to come a bit later on because it changes the way that we implement the noise. And for now, we only really need to worry about a simple noise just so that we can see the effects of our self-shadowing. So in terms of our blueprint, there's not a lot that's really changed here. We've just got some new parameters exposed, which is our shadow density, our noise scale and power, and the fog color, extinction color, and shadow color, which are all fairly self-explanatory. If I drag up my shadow density, obviously my shadows become more intense, and you end up with these more highlighted edges. The noise scale just changes, of course. The scale of the noise and the power will change how much of this noise erodes away the original fog shape. The fog color is, of course, the fog color, and the extinction color is the color that the light sort of goes extinct, or the scattering coefficient of the light, if you will. So if we change this, we can see we could get like a nice blue, and it falls off from this color through into the shadow color as well. So if we had blue here, for example, you could change the shadow color to be anything that you wanted. So we could have this as like a turquoise, but obviously that looks a little weird. So you could do what you wanted here, but for now we're just going to leave this as black. And for the blueprint, that's basically everything that's changed. There are a couple of extra parameters inside here, which we'll take a quick look at. So the flow speed just affects how quickly this rises. And as you can see here, we have this sort of aliasing artifact on the edge now. And this is caused by when we do our shadow trace, we're tracing outside of this shape, so we wouldn't be shadowed, and inside we would be shadowed. And because of the temporal reprojection of the fog, these are being jittered in and outside of this volume here. So that means that they are shadowed and unshadowed continuously, which gives you this sort of aliasing artifact. So we can fix this. There's a Boolean parameter that I've put in here, which we'll talk about later on. But if I click ignore base shape, then you can see that this has now changed, so that we're now no longer using the base shape for our calculation. We're just assuming that there's fog all outside of here when we do our shadow trace. And you'll notice that that's also broken this one over here. But that's because this has no noise applied, no height fall off. This is using purely a volume texture for its base shape, and it has nothing else. So by ignoring the base shape, it means that we don't get self-shadowing on there. But that's not really an issue, because you should only be using this volume texture to define a very basic shape anyway. We'll be using your noise and your height fall off to do actually add all the detail into there. So that's not really important for that. So it's not a major issue, again, if you use the fall off from the edge of the box. So if I increase the edge fall off here slightly to something really small, then you can see that basically goes away. Even if I turn this off, you can see it's slightly here, but that gets rid of it anyway. So if you're using an edge fall off, that's not too important. Something to note though is if you're using your box shape and we've got a height fall off and you're using edge fall off, if you put this box at the base here, you're going to lose a little bit of fog at the bottom because we're obviously falling off from the bottom of that shape as well. So I just have that lined so that the center is on your terrain or whatever you're using there. So that's just something to note. The other couple of things we have in here are shadow trace distance and shadow fall off distance. Now the trace distance is just how far we step in the light direction to take our offset fog sample, which we'll talk about when we talk about the theory of self-shadowing. And then our shadow fall off distance. So we just make the shadow density actually fall off over a distance too, so as we zoom out, then we don't get these weird stepping artifacts, which you can see here on this one, but it gets much worse as you get further out. But because we've scaled this by a distance, then that disappears as we reach the end of our fog distance as well. So you can kind of see it a little bit here as we're coming in, and a bit here. But if we don't scale that, it becomes much worse. So as I was saying before about the self-shadowing adding the visual fidelity that we need, if I change the extinction color here back to white, and I change the shadow color to white as well, then you'll see that it's actually very hard to see that noise that we've got going on. You can see it if you look sort of through the volume, but without the shadowing, it's very difficult to see. And so when we add our interaction, which some of the effects are very subtle, then they're almost invisible without the self-shadowing, which is why I said it's important to add it at this stage. So if I turn that on, you can see now that we've actually got noise and that it's moving, whereas before it didn't. You couldn't even see any of that. So that's basically everything that's changed since last time. We'll talk about the self-shadowing now, and then we'll go in and we'll break everything down and we'll look at how to implement this. When it comes to implementing shadowing on a volume, you may have heard of ray marching before, and that is essentially what we're going to be doing, but just a simplified version of that. So for ray marching, what you do is, if you want to know whether your point is in shadow or not, you need to know the density of the volume between your point and the light, because the more density there is, the more light will be absorbed or blocked by that volume to your point, so the higher the shadow density at that point would be. For ray marching, what you do is you take a number of steps towards the light, in the light direction, and at each one of these steps you sum up the density, and then you use that as your final density between your point and your light, and use that to calculate your shadows. For this, we're just going to be taking one step, so just a simplified version of that. We don't really need more than this, because one step adds the visual fidelity that we need, and any more than this is going to start to get very expensive very quickly. And also it means that we would have to mess around and implement our fog function inside of a loop, which can get quite complicated. It means we'd either have to do that in HLSL, or there's a couple of other ways around it, but we're not going to worry about that. We're not interested in that. We only want to take one step. So that's what we're going to look at when we look at implementing the self-shadowing. I just thought it was important to talk about that now, so that you get a bit of an understanding of what we're going to be doing. So we're basically just going to be sampling our fog function as we normally do, and then taking a step in our light direction, sampling it again so that we know the density of that point and how much that point is going to block the light to our current point, and we use that to calculate our shadow density. So as I said, we'll break all of that down when we actually look at doing it, but that is the theory behind it, and I just think it's important to explain that first. So all the changes here, of course, happen pretty much at the material level. The only thing that changes in the blueprint is we just expose those parameters again as we did last time. So we'll open the material up and have a look at it. It's going to look very different again now, but again, I'll talk you through it, so there's nothing to worry about. This is all to do with the self-shadowing. So before, you will have had this, which is excluding these two here, and this, which is the noise and that static switch I talked about. So ignore those. You have your base shape, your height fall off, and your global extinction, and that would be plugging into your extinction pin. So you just want to take everything that's currently plugged into your extinction pin in here and just copy that into a new material function. So just go to materials and textures, create a new material function, call it whatever you want. I've just called it fog extinction for now. And then when you open that up, just paste everything in there and plug it into the output. You can call your output also whatever you wish. You'll also notice that there's a huge chain of stuff going on here. And this just replaces everything that was world position before. We now have our world position as an input, so we can sample it at multiple different positions for our shadow sampling. So anything that was world position before, I've just right click and you create a new, if you can spell, create a new function input, make sure it's a vector 3, and call this whatever you want. I've just called it sample position. And you can also use preview value as default and plug world position in here, which just means that if you don't connect anything to the input pin of this function, then it will use the world position as a default value anyway. So once you have that, we'll just delete that for now. Just replace anywhere that had world position before with this input, and create reroute nodes, do whatever you need to do to keep it neat. As you can see, man, this is just a huge like spider graph now. This goes all the way over here, and it just replaces, as I said, anywhere that there was world position before, just plug that into it. And that is everything in terms of the inputs. The boolean here is also an input for the ignoring the base shape, but this isn't something that you might need to implement. It's completely up to you. If you don't mind having that aliasing at the edges and you're using the edge fall off, you can completely ignore this. So that would just be your multiply just plugged straight through into your global extinction before we talk about this. So you can ignore that if you wish, but if not, then all we're doing here is when our boolean ignore base shape is true, we're just taking our height fall off here before it's multiplied by our base shape over here. So we're ignoring our base shape, and if that's false, then we're obviously taking the product of both of those. So that's all that does there. That was just merely for an example purpose more than anything. So as I said, you can leave that out if you want and just leave your base shape in the calculation. But in terms of the noise, it's really simple. All we need to do is we'll grab the noise texture that I'm using. So in the first episode, I said to enable the volumetrics plugin. So if you've done that, then go down to your view options and make sure that you have show engine content enabled. And then you can scroll down, find volumetrics content down here, and go into content, volume textures, textures, and then there's a bunch in here, but we're just going to use the Perlin-Warloy balanced. This is really good for doing clouds and fog and all kinds of other volumetric stuff. So we're just going to grab that one for now, and you could just grab that and drag it into your folder here and click copy here, so you have a copy of that. And then you don't accidentally mess with it and delete it and do all kinds of other things. So that's probably the best way to do it. Just make sure you have it in here. And then you can drag that into your function and you'll have a volume texture sample. And all we're worried about doing is multiplying this by our result again. So you could do this at the end or before your global extinction. Again, with multiplication, it doesn't matter. And our world position, again, plugs into this. Ignore our rising for now. So that just goes straight through, and we divide this by a scale. So this means that this will cover 1,000 world units. Because we're taking world position in here, if we tile our texture without dividing it, then that means our texture is going to repeat every one world unit because UVs are 0 to 1. So by dividing this by 1,000, for example, it means that we're now just going to tile over 1,000 world units. So this is a direct world unit input scale for your texture. And we then raise that to a power also, which will increase or decrease the fall off. So we'll get noisier, more isolated shapes the higher the power is, and lower, softer shapes the lower the power is, so less noise basically. And by multiplying that power by the inverse of our density, what we're doing is we're getting noisier shapes in the less dense areas and less noisy shapes in the more dense areas, which just means that at the bottom of our volume, we're not eroding a load of it away, we're just eroding from the top softer areas, which gives us that nice fall off towards the top. And then, as I said, we're just multiplying that in. And in terms of the rise, it's very, very simple. We're not going to look at the full flow because that means implementing a flow mapping technique, which is a little bit more complicated and not really necessary at this point in time. It's something that we can come back and do later. So for now, we just add a bit of a rise to it, just so we've got some movement in there. And to do this, all we do is have our world position input here, and we just subtract the up direction multiplied by time multiplied by a speed. So that just means that we get this slow rise over time. And in terms of the noise, that's really all we need to do. The reason this is all wrapped up into a function is so that we can sample it from multiple locations for our self-shadowing, which we'll take a look at in a minute. But in terms of the fog, that's everything that you need to know for the extinction, sorry, not the fog. So I'll leave that for a second, and as you can see, I'll just scroll back over it just so that you don't miss anything. But just make sure you replace your world position input, and you've added your noise texture. You multiply this in, and we add this bit of rise, and that's all that's changed. As I said, you can just ignore that. So back in our main fog material, we'll go ahead and I'll break this down, and we'll talk about the self-shadowing bit now. So back in our main material, we'll have a look at how we implement this self-shadowing. And as I said before, it's very simple. It's just a case of taking two samples of our fog and then using this to calculate a shadow density, which then just drives a lerp between multiple colors. This is just our shadow fall off over distance, so we can ignore that for now. and then this is where we take our two offset samples. So for this, we are using the sky atmosphere directional light. So as I said in the first one, in this scene I have a sky atmosphere, and you just need to make sure that you have your directional light, which is set to movable, and it also has sky atmosphere light turned on, so atmosphere sunlight down here. And that means that we can really easily access inside the material the direction of that light here by just typing in sky atmosphere, and you can get the light direction. And that gives us the direction towards the light, not the direction that the light is pointing. So that means that as I move this around in the scene, so as I use Control L to pan this, you can see that our shadows update correctly and it shadows from the right position. So that's the way that we're setting it up for this example. You could do this with point lights or with spotlights or any kind of light you want, but it makes it more complicated. That's something that we will look at further down the line in the tutorial series. So if you want to know how to do that, that will come a bit later on. For now, we're just worried about implementing this using the directional light, because we just want to get the fundamentals in place here, and then we can worry about all the finer details a bit further down the line. So we just take that direction and we normalize it and multiply it by distance. So we now have a direction and a distance, and we add that to our current world position. So we're starting at our world position, and then we're moving this distance towards our light, and we then just sample our fog extinction function again at that position, which gives us the density of our fog between our current point and our light. And we use this in an exponential density node because shadows themselves are also exponential in nature. So you plug that into your depth, and then our density multiplier will be a shadow density parameter. This result is inverted, it says so in the tooltip. So we saturate this just to make sure that we're between 0 and 1, and then we invert that result. And we then use that to lerp between a fog color and a shadow color. And we also lerp between extinction and shadow, which gives us that fall off of that colored band in the middle there. So you could just have a shadow and a fog color, so you just plug that into B if you wanted, but obviously having the extinction color just gives us that nice effect there. This isn't a physically accurate way of doing it, but it does give us the result that we want. So for now, this is good enough. We then just lerp between our fog with our shadow contribution and just our fog color, so fog without shadow contribution, over distance. So we just take the distance between our points position and our camera position and just divide that by a fall off distance again, and that just gives us that nice fall off over distance that helps to avoid some aliasing artifacts. If you have fog that's heavily shadowed at far distance, it will begin to just look a little bit weird, and I'll demonstrate that now, and we'll just have a look at these couple of parameters in here. So the shadow trace distance we'll talk about first is important. This needs to be pretty low, because if this is, say, 100 units high, and we're asking our shadow to trace 100 units up, then the ones at the bottom here are going to start their shadow trace or do their shadow trace above where the fog ends. So we're going to get no shadow contribution at all. So if I set this to like 1,000, for example, it's just going to go white. If I set this to really small, then you'll get a similar result to if it's really large, to if it's just a medium value, sorry, like 10, not really large. As you can see, there's not a huge amount of difference there between 0.1 and 10. So have this in a small range, but whatever you have it at is up to you, obviously. And then our shadow fall off distance, I've just set this to the same distance as the render distance for the volumetric fog, which just means that as we get further away, you can see we lose that shadow contribution, and the fog then disappears as well. So that just helps to alleviate some of those temporal artifacts that are at the edges. And then it's just a case of exposing any of those new parameters that we've created inside here to the blueprint again, as we did last time. So in your set fog mid variables function, or however you have it set up, as I said before, we have ours wrapped in functions in here. We just add these to the fog settings here. So it's just these 6 here that we've added in this case. And just make sure those are added and exposed, and you put those under the category that you want, and then you can have a play with all of these yourself and find values that work for you and work for your project. So I hope that was helpful, guys. In the next part, we're going to look at the actual interaction, which obviously is the main point of this whole tutorial series. So that may take me a little bit longer to implement and get a video out on, but I'll try and do that as quickly as I can. And hopefully I will see you in that next part. If this was helpful, please let me know. And if it wasn't, also please let me know, and let me know why it wasn't too. So thanks, guys. Like and subscribe, and I will see you in the next one.